Hey there, thanks for tuning in. This is Mrs. J, and I want to talk to you about Introduction to Electricity. So you're going to be able to take notes from this video, or it might be easier, two other ways to do it. You can log into Project Lead the Way and look for activity 1.2.3 Electrical Circuits Physical. This is Principles of Engineering class, and look for that. Or you could just type electricity in this box and it will take you here. So I'm in Introduction. That's where you want to go. Okay, the other thing is I'm going to share these slides with you, and they have basically the same information, just enough to get us started. So these will be in Google Classroom. You can take your notes from there. You'll have to write these in your notebook when it has like a flip grid question. Okay, so let's hide those. Let's take a look over here. So Intro to Electricity. This is Project Lead the Way. I love this lesson, so I hope you enjoy it too. We're looking at electricity, and it's a type of energy that lets you have a flow of particles. So we've got particles with a charge and they're moving, and it's their movement that gives us this electrical energy. If you click on the bold ones, you'll get a definition that you could put in your notes. Electrical energy is energy caused by the movement of charged particles. So we can transform them into many forms that are useful to us, like light, heat, sound, motion. Electrical energy lets it have the ability to be converted, stored, transmitted, and reconverted efficiently into other forms of energy. So we're going to look below it, look at some other energy down here. So we got static, solar power, solar panels giving you solar power. What we're going to look at are the three main properties. It's fairly simple. Current, which gives you a net transfer of electric charge. So that's when the electrons are moving along a path. I'll show you some videos so you can see it'll make more sense. And that's over time. So how fast does it go? How slow does it go? How much current can I get? But it's always movement. Current is always movement. For voltage, we're looking at potential difference. What could happen? And it's measured in volts, which is easy enough. It's also the amount of work to be done to move a charge from one point to another along an electric circuit. So while that current is moving, what sort of work has to make it move? The voltage is that work. And then we have resistance. That's what's to calm everything down. So it's the opposition, like friction would be, it's the opposition to our force that a device or material offers to the flow of direct current. So it wants to slow it down so it doesn't get overpowered, it doesn't explode or just cut off on us. So we want to make sure we understand the relationship between current, voltage, and resistance. And this helps engineers to design efficient, safe, and functional electric circuits. Safety is the main concern, and also function, because if it underperforms or overperforms, you have more issues. Okay, so they're made up, electrical circuits. They're made up of an energy source to provide voltage. They have conductors to allow the current to move along or travel. And then they have insulators to limit the current travel, and a load. So electrical circuits provide an uninterrupted path for current travel in two distinct categories of design: series and parallel. So when you are taking your notes, please click on those and have these in your notes. Series is when you have everything connected end to end. It gives you a single path of current. An example would be like if you do holiday lights for any sort of holiday, and you notice that one light bulb goes out, or it gets broken, or your dog chews one light bulb, the whole string goes out. Those are in series. But if you have them in parallel, it's a little bit different. It's a closed electrical circuit, just like the other one, but in this one it has the current divided into two or more paths. So if your dog were to chew the little light on a holiday light, like for Halloween or something, they could still stay on. The rest of them could stay on while that one goes out. So it says the current is divided into two or more paths and then returns via a common path to complete the circuit. And we're going to do exact specific math on the current, so maybe you'll understand that when you're working that out. For careers, we know about electrical engineers, but you need to know a little bit about electricity to design any sort of a system so that you don't override whatever else you're working on. If you're working on something mechanical, you need to have electricity with it. So an engineer has to have like a basic knowledge of that. Okay, so now we're going to look at how electricity works. So how does electricity work? We're going to compare an electrical circuit to a water system. So two different systems, we're going to compare and contrast just to help you understand. So when you have water, we put water in a tank, and then the water flows to the pipes. So you got it in here, turn on the faucet, water flows through, easy peasy. The water flow can be stopped or allowed to go by turning that faucet. Potential energy of water can be converted into kinetic energy through a water wheel. So they're saying potential, the water's flowing. When it hits this wheel, it makes it spin. You can use that spinning motion to drive a machine. So that's potential, waiting to go, and kinetic, actually moving that wheel. So then they're going to compare it over here. I don't like comparing water and electricity because they don't belong together, but whatever. In a similar matter, electrons can be stored in a battery. So you pick up a little battery from the store, it's got electrons hanging out all over the place. They're going crazy. The electron flows through your wires. So we've got wires here, so you're going all the way around. Electron flow is stopped or allowed by a switch. Doesn't ever get to trickle like water. On, off. On, off. No trickling, because then everybody dies. So electrical energy can be converted into light and or thermal, because you get some heat out of that light, right? Through a light bulb. So light energy or thermal energy through a light bulb. It says end, but now we have cool light bulbs that don't get hot, so it's got to be end or. So similar, right? Electrons flow through the wires, on, off, turn on the battery. Water in a tank, on, off with a handle, make something move. That pressure makes something move. So I don't know, but it's pretty cool, huh? All right, let's look at circuit components. We're almost done. So in all electrical circuits, we want to look at circuits. It's our system, how conductors and components form a complete path for the current to travel. We always want a closed system, otherwise it doesn't work. So the circuits have basic components: a source, a conductor, a load, and sometimes a switch, because you could just plug it in without a switch and it could work. The electrons must have a continuous path from the source through the circuit and back to the source. In this case, our source is a battery. They say otherwise it's like water flowing through a pipe that's stopped at a blockage. So something's stuck in your drain, the water can't go, you're stuck. They keep comparing it to water, but they're two different systems. The circuit cannot be completed there. Okay, so let's take a look. We have our source, that's the battery. We run the electrons through the wire and they don't get to move until we turn this on. So please ignore this faucet and pipe they're trying to compare, just ignore that. So we flip the switch, we turn it on, and the battery says, okay, I'm going to run. And it runs to the light bulb. But it also has to run back from the light bulb to the other side of the source. Without this wire right here, it cannot connect. And that's why the circuit has to be a closed system. All right, so when you're looking at an electrical circuit, you want to draw this in your notebook. You want to start to understand a schematic. I know many of you have some background in this, but it's still confusing, so I would still draw this in there. Draw this part right here. You want this center part, and this is the thing we want to understand. So an electrical circuit is drawn using industry-specific symbols. The circuit represented earlier, blah, blah, blah. Okay, who cares? Let's look at this stuff. See the long line and the short line with the minus and the plus? That indicates that you have a power source. They have it on the side here, but it's usually written this way, and this whole thing would be rotated. I think they were just trying to fit it nicely. So we have our line here with the short one, a long one, and a minus and a plus sign. You'll find when you get into electrical engineering, if you do, or if you study a little bit more in college, how many lines are in here make a difference to what size battery you have. For this course, we just try to draw the symbol. So we draw the wires, indicating our circuit, and then we would add a switch. The switch generally looks like this one on the right. We show it as open because when you draw it closed, you don't really know that it's actually a switch. It just looks like a line. So this is more of what we're looking for. The resistors are fun to draw. That's this right here. And I'll teach you how to read the colors so that you understand how to use the correct resistor. If it's too small, your light bulb will pop. If it's too large, your light bulb won't turn on. And they're physically the same size, so it's just a matter of reading the color codes. And then this here is a symbol for a light bulb. We're going to change that symbol a little bit. This is a little old school right here, but they're just trying to show you. When they say light bulb, they mean a little LED. And then this is a wire, the regular wire. So you want this, and you want to label everything. Battery, switch, resistor, light. So see if you can put that in your note, nice and neat. Use a ruler, start to understand that. And then one more tricky part, and we'll stop here. So please set this up in your engineering notebook. It's something that looks really, really simple, but once you go to put it into practice, it becomes confusing. So we already start to understand what voltage, current, and resistance are a little bit, right? We had an intro. That's the quantity that we're looking at. They each have their own abbreviation. Voltage has an uppercase V, current has an uppercase I, and resistance has an uppercase R. I forgot why it's an I. Something to do with some Latin word, illumin or something like. You can Google it. Sorry, I don't remember. But then we have the units that they're measured in. So a voltage with the abbreviation V has the unit of volts. If I measure something, I say, oh, it has 3.5 volts. And then I use the symbol as V for volts. For current, this is the one that gets everyone tricky. It has an I as an abbreviation when you're talking about the word current. But when you measure, you're measuring in amperes or amps, as you're probably familiar with. And for that, we use an A. The way I try to have students understand this is, let's compare it for length. Let's say I wanted to measure my hand. I'm probably going to measure it in inches. I'm going to get a ruler and say, oh, my hand is 7 inches long. So I measured length, that's my quantity, which I could abbreviate as L. You know, when you put height, width, and length, you put L. But my unit would have been inches. It could have been centimeters, it could have been miles, could have been whatever, but my unit was in inches, and that had the symbol IN. So if that helps you compare this, maybe you'll start to understand that. So current, I, has the unit amps or amperes and the symbol A. For resistance, we have the abbreviation R, and we use ohms with the cute little Lululemon sign over there, no omega. Put that in there. So get this in there, start to understand it, and we'll look at some calculations next time. Thanks for hanging out with me. By the way, if you have access to Projectly, the way you can do it right from here, because then you can play around with all the little bubbles you can plug in. We'll do this next class. Thanks for watching.